Good morning, good afternoon, and good evening, and welcome to the NRIC Tech Talk, Irradiations for Advanced Reactors. First off, I need to turn this off really fast. Sorry. My name's Steve Grabinski, and I'm a project manager for the National Reactor Innovation Center. Before we get started, I want to go over a few items to help you participate in today's event. For the best experience, turn off any VPN or Citrus connections. Please ensure your audio and visual are turned off during the main event. Please submit any questions by typing your name, typing your question into the chat in the section of the control panel. You may send questions at any time during the presentation, and we will address them during the Q&A. For any technical issues, please email Eric Schuster. His email address is in the chat section of the control panel. I'm sending that now. For any programmatic questions, please send an email to nric@inl.gov. This event will be recorded and provided on the NRIC website. Your participation is consent in this recording. NRIC set up today's event to help inform the advanced reactor community of the capabilities of our nation's 4 test reactors. We hope this presentation will help the community understand the importance of materials and fuels, why we test them, and each reactor's capabilities, and also how to best take advantage of those capabilities depending on the scopes of the community's desired experiments. Each speaker has a wealth of knowledge, and we encourage you to ask them whatever questions you have. And any questions that we don't get addressed today will be published on the NRIC website. In the interest of time to cover all the technical presentations, today's speakers will not be talking about the funding mechanisms for irradiations. But I want to take a moment to share some high-level ways developers can begin seeking funding opportunities. First, NRIC has a program called the Resource Teams. This program provides 200 hours of subject matter expert support throughout the National Lab Complex and could be a mechanism for scoping experiments. However, the support cannot be used for any previous federally funded program or experiment. For more information, please contact our NRIC Technical Program Manager, Sam Reese, and I'm dropping his email in the chat right now. Second, NRIC's sister organization, the Gateway for Advanced Innovation in Nuclear, or GAIN, has collected several different funding opportunities, and I'm posting that link in the chat as well. For any questions on IFOAs, vouchers, or other agreements, please reach out to Chris Losey. His email is also going to be in the chat. Finally, I wanted to announce that registration is open for the U.S. Department of Energy's Office of Nuclear Energy for fiscal year 23, the Consolidated Innovative Nuclear Research Funding Opportunity Announcement webinar. This webinar will provide information on CINR's work scopes and FOA updates. This will also include information on NE's priorities, programs, and other university-focused opportunities. The webinar is from August 9th till August 11th. And I'm dropping the registration in the chat as well. And now I'd like to introduce today's speakers. In the interest of time, their biographies will be found on the NRIC website. One moment. And that was during the registration of today's event. So to open our event, the director of the INL Nuclear Fuels and Materials Division, Dr. Steve Hayes, will provide an overview on developing new fuels and their need for test reactors. Nick Wolstenholme is presenting the Advanced Test Reactor, or ATR, and currently works in the Nuclear Fuel Design Department at INL. Dr. Colby Jensen is the technical lead for transient testing at INL and the DOE Advanced Fuels Campaign. Dr. Jensen will be covering INL's Transient Test Reactor, or TREAT. Dr. Chris Petrie is a senior R&D staff member and leads the Advanced Fuels Fabrication and Instrumentation Group of the Nuclear Energy and Fuel Cycle Division at Oak Ridge National Laboratory. Dr. Petrie will be covering the High Flux Reactor, or HFIR, High Flux Isotope Reactor. Dr. Gordon Kosey is the Managing Director of Operations for the Massachusetts Institute of Technology Nuclear Reactor Laboratory. And now I will pass it to Steve Hayes to begin the presentation.
Thank you, Steve. Can you hear me okay?
I can, thank you.
Okay. So I don't have a lot to say, but I'm going to set the stage for the speakers that will follow by talking about the need for developing new fuels and what role test reactors play in that process. Next slide, please. This is an outline of just a few things I want to cover: the importance of developing new fuels, the role of irradiation testing in fuel development, look at the traditional fuel development timeline, and talk about the need for accelerated testing and qualification. But I'll be making the case that even with new accelerated approaches to fuel qualification, we're still going to need the use of test reactors. Next slide, please. So I'll start with the importance of developing fuels. And I'm a fuels guy, and when a fuels person says fuels, it means fuels and materials. So I say fuels, think of fuels and materials. You know, not every fuel is appropriately suited for every reactor applications. We have a handful of fuel types that we consider qualified and available for use, but they're not the right fuel for every reactor. Perhaps you want to change reactor's coolant, and a given fuel just isn't compatible with that coolant. Importantly, some fuels play an important role in the enhanced performance or even safety of a particular reactor design. I think of a couple like UCO triso as envisioned for use in gas-cooled reactors, or metallic fuels in sodium fast reactors. These are fuels that not only work or acceptable for use in those kinds of reactors, but the inherent properties and performance of them actually contribute to the reactor's safety posture. And that's a great thing when it's possible. You know, when we look ahead to advanced reactor designs, we have to go into it thinking, you know, there are some advanced reactor designs that could benefit from new fuels with unique properties or performance that mesh well with a particular reactor. So the conclusion here is the design of new advanced reactors should actually motivate the continued development and qualification of new fuels. Next slide, please. What's the role of irradiation testing in fuel development? Well, it's an integral component. It's an indispensable part. The picture on the right shows what we usually think of as the traditional fuel development R&D life cycle. It starts with fuel design. You come up with an idea for a fuel concept. You figure out how to fabricate it. You characterize it. And then you move into testing. And probably the most important part of that testing is irradiation testing in a reactor. Out of the reactor, you're going to do post-irradiation examination, PIE, to see how it worked. And almost certainly going to want to change something to improve behaviors you saw in the reactor. So you go into this this development cycle again. Now, all the while you're developing your fuel performance code or modeling tools to help you understand what you're seeing and use an analysis as you move forward. So irradiation testing is a critical part. It's used in the early phases to assess phenomena envisioned to impact feasibility, fuel lifetimes. You know, initial experiments are often times very simple and often quick. As the design matures, irradiation testing is used to determine sensitivity of performance to fuel design, fabrication variables, operating conditions, and ultimately to establish burn-up limits and quantify safety margins for various operating conditions, both normal and off-normal, and ultimately nearly prototypic experiments are used to demonstrate that fuel or fuel assembly behavior is within the bounds of some safety case that you're making for a regulator. Now, while it is possible to perform some of these kinds of tests in NRC licensed power reactors, it's generally very difficult to do that. And DOE authorized test reactors, which are well, they're designed for this, and they're just ideally suited for this purpose. Next slide, please. About 15 years ago, a group of DOE fuel developers took a look at the way DOE developed and qualified new fuels. It looked at the DOE world, but the conclusions hold for the commercial world as well. And what they found is it takes about 20 to 25 years to develop and qualify, obtain authorization for use of a brand new fuel type. That is using the traditional historical fuel development process, which tends to be very empirical in nature. It makes use of extensive steady state irradiation testing to bound all operating conditions, accumulate statistics, and collect data for validating fuel performance codes. And in the same way, you typically have to do transient tests to bound all off-normal conditions. Now, well, even thinking about the current fuel qualification program DOE is engaged in right now, qualifying UCO TRISO fuel for gas reactor use. When you look, when all's said and done with that DOE program, again, it's probably going to take 25 years to make it through that cycle. Now, that's not good news. And in fact, those of us who've looked at that have concluded that such a long and costly fuel development timeline tends to stunt design innovation for new reactors. A new reactor designer doesn't want to on development of a new fuel that may be ideally suited for his or her reactor because it's just too consuming and expensive. And so the punchline is we really do need some sort of accelerated fuel testing and qualification process to support advanced reactor design and development. Next slide. And this is my last slide. And just following up on that need for accelerated testing and qualification by fuel qualification, let me just make sure you know what I mean when I refer to that. It means regulatory approval for using a specific fuel design in a specific reactor under a specific set of identified conditions. So almost no fuel has a universal license. It's authorized for use in particular reactors under particular operating conditions. And as we look ahead, those of us in the labs and with some industry partners as well are already talking about ways to accelerate fuel qualification. And there'll probably be a lot of things that make up this approach, including accelerating the time it takes to test fuels and test reactors, which can take years. Expanded use and impact of in situ instrumentation in reactor experiments, high throughput PIE methods, development use of state-of-the-art mechanistic predictive modeling and simulation methods. But we'll also be looking to work with regulators to develop and use novel qualification and regulatory approaches. The bottom line, though, is even as you hear talk in coming days and years about work towards accelerating the fuel qualification process, it may be the case that the number of fuel experiments required goes down or the nature of experiments change. But let me assure you, the need for irradiation testing of fuels and materials and test reactors will continue, and that's the message. And the rest of the webinar will be highlighting the premier test reactors in the US available for doing this kind of work. So I'll pass it off next to Nick Woolstenhume.
Thanks, Steve. Can everybody hear me?
I can hear you.
Yes.
Excellent. All right, appreciate that introduction, Steve. Let's launch right into it and give you a quick introduction to the Advanced Test Reactor. I'll go ahead and advance to the next slide. All right, so, oh, Stephen, it looks like I had an animation in here. Click so that MTR, ETR, and ATR pop up. I was a fool to include an animation. So the Advanced Test Reactor was constructed in 1967. I like to say that it's a third generation in 3 landmark material test reactors: the material test reactor, the MTR, the engineering test reactor, ETR, and then finally the advanced test reactor, ATR. So ATR is kind of like MTR's grandson, I guess, and it shows in the design. This really was the pinnacle of material test reactor technology in what I think of as the golden era of American engineering. You think about 1967, this was the era of SR-71 spy planes and Saturn V rockets. So really some neat things came out, some of engineering's best accomplishments, and ATR is on that plane. It really is that kind of machine. So, you know, it's 50 years old now, actually a little bit older than that, and remarkably is still advanced and really remains the nexus of fuels and materials research in the nuclear community. Go ahead and go to the next slide. So a quick background on ATR. It is generally thought of as a high power density reactor, approximately 1 megawatt per liter. This is specially enabled by its core design. It is a pressurized water reactor, but maybe not the kind of pressurized water reactor you would think of if you were thinking of like a commercial plant. And that's because the pressure isn't quite that high. It's just a shade under 3 megapascals, and the water temperature is actually quite cool, about the temperature that of a bathtub, I suppose, about 60 degrees Celsius. It has aluminum-clad plate-type driver fuel and very high coolant velocity, upwards of 15 meters per second. So essentially, the whole thing is the whole machine is designed for this high power density. And you see it all over in the design of the driver fuel and its primary coolant system. Other remarkable features are a rotating drum type control mechanism that allows it to have a very smooth chopped cosine axial flux profile over its 1.2 meter long core. It's a pretty long core for a material test reactor. This control drum scheme also allows it to have a large power tilt across the core, so one flux trap can be running 3 times higher power than the other if needed. Has a high capacity factor, at least for an MTR, maybe not compared to a commercial plant, but for a material test reactor, we typically run 60-day cycles and over 200 effective full power days per year. Very recently, its beryllium reflected reactor was replaced, and there were some other refurbishments performed. You know, the facility is planned to operate for decades to come. Next slide, please. So one of the most iconic things about ATR is its so-called serpentine or cloverleaf shape of the core, where the driver fuel kind of winds around in that shape you see there. This creates 9 flux traps. These flux traps are rather large and rather high flux. 6 of them are presently in permanent use for pressurized water loops. So they have their own independent chemical and thermal hydraulic environment. And then there's other flux traps that are available for other kinds of experiments. And then there's numerous other test positions in the inner core, and the inner reflector, and then outside and kind of the outer reflector. So spanning orders of magnitude in flux. Unmodified, the neutron spectrum in an ATR is roughly a 1-to-1 thermal to fast ratio in the inner core, and roughly a 10-to-1 thermal to fast ratio in the reflector area. Next slide, please. So rather than focusing on ATR's kind of hallmark capability, that is its pressurized water loops, this particular presentation is really focused more on all the other things that are perhaps a little less celebrated about ATR, trying to give you a different perspective for advanced reactors. And I don't mean to imply that water-cooled reactors aren't advanced, but just trying to provide a different perspective of ATR, perhaps if you are looking to develop fuels and materials that are not classical LWR type application. So we start from what we call a drop-in capsule. A drop-in capsule is really nothing more than a tube or some sort of containment boundary that has specimens in it. There are numerous examples of how to do this. I won't show you all of them, but I think the main thing to say about this is that we can irradiate very small specimens, things the size of a toothpick. We also have test positions that are large enough to irradiate very large test articles, you know, the size of like a 2-liter soda bottle. Just trying to think of a food-related size geometry you might be familiar with. So the whole thing with these drop-in capsules is that typically one uses a gas gap between the specimen and the outer wall of the capsule to create a thermal resistance, so that gamma heating and/or fission heating in the specimen drives its temperature up, and really virtually any relevant temperature is achievable just based on how you adjust that gas gap. And so really a utilitarian way to do a cost-effective irradiation. One of the downsides to a drop-in capsule, of course, is that you don't have direct monitoring or instrumentation or control of your boundary conditions. But there are options for passive dosimetry and temperature monitoring. And generally speaking, I guess the way to think of a drop-in capsule is that it's a great way to get first data. It's efficient in terms of cost and schedule, and as a result, ATR is a real workhorse for drop-in capsules. Next slide, please. So another good example of an advanced reactor supporting irradiation strategy in ATR is what we call a gas lead-out. Essentially, imagine a thimble tube that penetrates the reactor pressure vessel, lets some existing flanges and penetrations made for this purpose, and then goes down into the core. And then plumbing lines connect it to gas monitoring and control systems that reside outside of the reactor vessel. Kind of the canonical example of this is the irradiations that Steve mentioned earlier for the AGR TRISO program. These are really pretty elegant, well-designed irradiation tests, and numerous temperature instruments, and sometimes even flux sensors read in real time, and the ability to adjust the gas composition in real time. So using like a mixture of helium and then a lower thermal conductivity noble gas to allow you to adjust the thermal resistance between specimens and the cold wall that's being cooled by the reactor coolant system. So it's really cool. You can measure temperature and adjust it in real time by this method. Also, with the gas system, one can monitor for radioisotopes in the exiting gas sweep and things like that. Another development that is underway that you perhaps might care about is we are working to design and install a helium-3 pressure control system at ATR. That will allow tests like this to vary not only the thermal conditions, but the neutronic conditions in real time. So by adjusting helium-3 pressure, one can filter out thermal neutrons and change flux delivered to the specimens for doing things like real-time adjustment, power cycling, things like that. So stay tuned, that's underway. Next slide, please. All right, so introducing kind of a new concept. We're calling it instrumented capsules. These are a type of lead out that we are presently working towards deploying in ATR. But instead of the very elegant gas lead out I just showed you, imagine a long, skinny capsule that penetrates through the reactor, and really it's like a capsule that you passively monitor. So our whole thought here was like, we have drop-in capsules. I like to call that the bicycle option. We have full-blown AGR style gas lead outs. I like to call that the Cadillac option. Sometimes people need something that's somewhere in between. So we've been endeavoring to create the Honda Civic option, and this is the concept of an instrumented capsule. Our first instrumented capsule design is presently under final design and slated for installation into the reactor in 2023, where we will be looking at advanced metallic fuel systems and monitoring their thermal conductivity evolution in real time with a novel thermal conductivity probe. It's also possible to change the spectrum in this test, in these types of tests, if one desires a faster spectrum. So in this case, we're using a cadmium basket to filter thermal neutrons. Go ahead and go to the next slide. We'll talk a little bit more about spectral modification. Yes, ATR is a thermal spectrum reactor, and yes, many advanced reactors are fast spectrum reactors. And presently, there is no fast spectrum material test reactor available in the United States and really in the Western world. So we have to get clever about how we can use ATR to mimic some of the important features of a fast spectrum reactor. Our tried and true method that we've done a lot and has been very successful is just to use the previously mentioned cadmium baskets. So we put cadmium foil inside of an irradiation basket and put capsules inside of that. This significantly reduces the thermal flux and does a lot to help flatten the radial power profile in a fuel specimen that might be intended for development in for example, a sodium fast reactor. We've had good success with this, but throwing away the thermal neutrons is only part of the battle. We would also like to increase the fast neutrons and do an even better job of this. And so one of the concepts that is currently under design under DOE's Advanced Fuels campaign is a concept where we use additional booster fuel in a flux trap to turn thermal neutrons into freshly born fission fast neutrons, and to combine that with thermal flux filtering. And presently, this thing is not the final design is not complete, but we've scoped it out enough to know that it is viable to achieve a thermal to fast ratio of about 1 to 100. So that's a very fast spectrum for a reactor that is innately a thermal spectrum reactor. So we're excited about that. Stay tuned, and as we look to move forward with better and better capabilities on the fast spectrum side, ATR is going to remain our workhorse for a while yet. Next slide, please. All right, I think I'll turn it over to Colby Jensen.
All right, great. So I have the pleasure to share a little bit about the Transient Reactor Test Facility. We call it TREAT. Next slide, Stephen. So the first, going back to Steve's introductory slides, I want to provide a little bit of context to the kind of the traditional reasoning to have a transient test facility like TREAT. Quite often, I think folks don't really consider a transient test reactor in the scheme of materials testing, but it serves a purpose, as Steve alluded to, in looking at how fuels and materials are going to behave under extreme conditions. So we say frequently we like to make the comparison to car crash testing for nuclear fuels and materials. This all stems back, of course, to the need when you're licensing a fuel system, qualifying a fuel system, and even developing a fuel system. Some of the important goals are to understand how it's going to behave under the range of conditions that it could experience, or even things that are postulated to be possible under accidents or other types of conditions. So we need to identify all these sorts of degradation mechanisms, the failure thresholds, and have a way that we can characterize them and predict them appropriately. An important aspect to this is that by doing so, you can actually improve your operational envelopes. You can improve your performance if you understand really where all these limits lie and how much margin you have to these sorts of things. So ultimately, the reason to do transient testing is that it's going to give you better economics in your design as you better understand the envelope that you can exist within in your operational space. So next slide, please. So this slide is sort of, I think, the treat facility in a nutshell. Some of the following slides, I'll hit on some of these points a little bit more. But if there's one takeaway slide, I think this is it. So the Transient Reactor Test Facility went operational in 1959. I think of the test reactors in this seminar, this is the second to oldest reactor. I think MIT might have it beat by 1 year. Operated from 1959 to 1994 until it went into operational standby, and operations were resumed again in 2017. So fairly recently, this reactor came back into our portfolio of tools for nuclear fuels and materials development. The reactor design itself, I'll just mention a few of the key takeaways I think that are important that help to understand how to use the facility. But the reactor itself is shown in the cross-section view at the right. The yellow there is the region where the core is, and the darker gray region inside the yellow is the actual fueled region of the core. In there, it's zircaloy clad graphite fuel blocks. Has a little dispersion of UO2 within that graphite that effectively is the fuel. The reactor is cooled by air blowers. The cooling serves no safety function. So that's a unique, I think, a unique aspect of this reactor as a test reactor. Virtually any power history is possible in the treat facility. The main limit that you've got to deal with when you're thinking about how to use treat is you have 2,500 megajoules of max core energy to deliver, and you can deliver it in almost any shape, form, rate that you'd like. I'll talk about that in a later slide. There's no reactor pressure vessels. So I already said it's air cooled, but that really doesn't serve a safety function. So this is a really nice aspect of the treat facility that facilitates things like in-core instrumentation, lead outs, putting things in and out of the core with ease. In general, it's very accessible. You have 4 viewing slots around the core that are shown also in the diagram at the right. On the left side, you can see what we call the hodoscope or the fuel motion monitoring system. And on the right side there, you can see what is the treat neutron radiography station. And then on the other sides of the core, there's a similar access that's currently not in use. So when we test specimens, as I mentioned, you can change the power as you'd like, but some transients you can drive to very extreme conditions, so up to 10 to the 17 neutrons per centimeter squared per second. It's very high flux. Total dose or total fluence is on that same order, so 10 to the 16, 10 to the 17 neutrons per centimeter squared. So really, that when you get that high of flux, you're not going to be running for very long at that condition. The experiment vehicles that we put into treat, can't see very well in the diagram at the right there, upper right, but it goes right in the center of the core, where kind of the white line is in the middle of the yellow. We replace some of the treat fuel elements with our experiment device, and we can replace those effectively as needed. So we can test any kind of environment that comes in through a test vehicle itself. The test vehicle contains the specimen. It has its environment, has the instrumentation. It all comes in a package that we drop into the reactor. When treat was restarted, it was really a project to address the facility refurbishment. The historic supporting infrastructure to do experiments was largely not available, so we've been in the works of regenerating and developing new capabilities over the last several years to make that happen. So treat's experiment history is quite diverse. The capabilities are quite unique, but today's world requires even probably more diversity than treat's historical mission required. So we've approached the experiment in treat using what we consider a modular, multi-purpose experimental approach. So I'll talk about that more in the next slides. Next slide, please. So just to give a little bit more perspective on how experiments might work in TREAT, at Wright, there's some more technical information and kind of what the flux profile looks like axially, as well as the neutron spectrum in the core. It's a very thermal spectrum, as you can see. Generally, TREAT experiments aren't in the reactor very long, typically just a few days at most. Maybe a little more than that in some cases, but generally just a few days. When we actually run an experiment, it usually lasts somewhere on the order of milliseconds to several minutes. We can do experiments where we run multiple transients, so multiple power histories are run on the same device over the span of multiple days. But regardless, when you look at how TREAT is utilized, the best way to utilize it, the fluence that you're going to get out of TREAT is not high. Using TREAT to generate high dose, effectively DPAs and materials is not a good use of TREAT. So what is TREAT good for? TREAT is best suited for testing fuels and materials that can interact with the fuels. So when you need nuclear heated fuel material interaction, that's where TREAT can really shine. If significant structural burnup or material fluence is needed, then you're better off probably looking at something like the other test reactors that are part of this webinar. Next slide, please. So reactor power control. I already talked a little bit about this. TREAT has a sophisticated control rod system, would have multiple rod designs as part of this control rod system that allows for essentially a very nimble control of power in an experiment. So we say, some people would say that we think of a transient reactor, we think of just doing pulses. TREAT is not a pulse reactor. We call it a shaped power history reactor, or sometimes I call them windowed power history. So if you think about some sort of a power profile that corresponds with some given reactor design, you look at some portion of that and you want to simulate that kind of an event, that's where TREAT can best suit your needs. So there's some examples that are shown on this slide. There's any variety of other examples, but things from power ramps over several tens of seconds. We see things like this example of a loss of coolant accident, where you might be operating at some power level and then lose coolant, and also your power drops off significantly. Reactivity initiated accident type conditions where you get some sort of a pulse. TREAT can do pulses as well. But then, the chart on the far right is just a made up power history that just to illustrate the point that really you can drive about any kind of power history that you want. Another really interesting thing I think about the TREAT control system approach is that it allows to accept feedback actually from experiment instrumentation, something that was used historically for unique benefits to a given experiment's needs. But essentially, signals from an experiment can actually trigger some control rod movement that drives a condition that's desired by an experiment. So it provides some talking back and forth, which is quite, I think, an interesting idea for some needs. I think there's a little animation, Stephen, and you can proceed on. Yeah, there's the giveaway. All right, so as far as the experimental infrastructure that we use in the test reactor, a given experiment needs to bring its own experimental infrastructure, its own device to be able to actually use TREAT effectively. Currently, today, we say we have essentially 5 main product lines. I added a 6th here because it's not really a product line, but it's something that's, I think, begun to really take center stage with some of the things we do at TREAT, is instrumentation and modeling platform. We've got a lot of work in light water reactor, sodium fast reactors, space nuclear propulsion. We're supporting national security missions in TREAT, but also, of course, the advanced reactor space is quite broad with several different potential interests, needs, and requirements. So, as I mentioned earlier, the experimental infrastructure is designed to be modular and flexible. So we have these different test beds, and typically what we see in each of these sort of test beds is we've ended up in two categories of test devices, usually a little bit smaller, more affordable scale type test device that's illustrated on this slide on the left, and on the right, larger scale test devices, such as this sodium loop that's shown on the right. So this is, we say, the cartridge in console architecture that is generally used in all of the testing that we are doing in TREAT today. So next slide, please. This slide shows some specific examples. I won't go into a lot of detail here, but from a few of these particular test beds, we've got in the last several years significant development, and some of these are still under development to be deployed in the next couple of years. But spanning the different scales that I just mentioned, you can sort of see that on the order of something that you can hold in your hands to something that you might require a few people to hold in their hands. But in thinking about any particular advanced reactor need, we have devices on the shelf that probably work to get things started, but as you get more into what you consider more prototypic conditions, you want more prototypic environments, it might drive you to develop your own sort of system to support a particular need. So next slide, please. So I think this is my second to last slide. Just want to make a comment about the instrumentation. I think this is maybe a little bit generic to several of our test reactors, but I mentioned that one of the advantages that we have in TREAT is good access to the core. It's not easy, but it's relatively very good access to the core. And we've done a lot of work in the past, what's now 5 years since the TREAT restart, to develop expertise and capabilities that allow us to make any variety of measurements in the reactor core under a variety of environments. So I show some examples on the right. Don't want to focus on those too much. These are some data plots of things that we've measured in a couple of experiments. Effectively, advanced instruments, ideas that you have for measurements is an important consideration when thinking about an experiment that one might want to perform. And I think we've got the people and the understanding that can help you achieve what you need if there's some particular data outcome that's desired. So we're actively using several of these tools, but it's part of our normal mode of operation to also develop, qualify new approaches as new needs come into the facilities. We've got the expertise and facilities to do that. Next slide, please. I think this is my last slide. Just want to make a few comments. I focused largely on the sort of what I would consider the traditional transient testing mission of the transient reactor test facility. But I think there's a few other ideas that I'll just throw out there that folks might consider. Some of these ideas are things that have been, I'd say, have begun to be explored in recent years and likely to continue in some cases. And some of these ideas are things that are very much still in a conceptual phase. But first of all, fission effects on material properties. So I mentioned the good access to the TREAT core. Something that's under investigation even currently is looking at how we can utilize this good access to see in situ behaviors, material property behaviors as you have fissioning happening in fuels. And making measurements on those things as it's happening. That's something that I think can really actually quite benefit the community. Nuclear materials under extreme conditions. So in general, you can go to quite extreme conditions. I already mentioned that in terms of some of the fuel performance types of issues that are of interest. but you go into very high temperatures. We design these capsules and things to be quite robust. The facility's set up to handle these kinds of extreme conditions, which are not common in most other facilities. Dynamic multiphysics instrumentation testing and model benchmarking. So TREAT is inherently a multiphysics environment typically. It's a great place to look at dynamic behaviors and interactions in these physics. And some of our experiments, almost all of our experiments generally lend well to that, but I think that there's opportunity to consider setting up unique things for that explicit purpose. And then the last one I'll throw out there is thinking about system scale core component test bed with nuclear heating. So this diagram at the right is a concept that is out there for how one could potentially take advantage of some of the unique attributes of the TREAT facility, like its automatic reactor control system that can be tied to the experiment to provide feedback and develop a better understanding of how these systems interact, but combined with nuclear heating, which is provides some unique opportunity as well compared to perhaps out of pile approaches. So with that, I think I'll end. Thank you.
All right, thanks. I'm Chris Petrie. I'm going to talk about the high flux isotope reactor. Next slide, please. Before I do that, I want to briefly talk about, the whole workflow of irradiation campaigns at Oak Ridge. It all starts out with irradiation design and engineering. That could be an off-the-shelf vehicle for performing an irradiation, or it could be novel, whether you're testing a new fuel, material, temperature, or other environmental condition. Irradiation testing can happen, and it can happen in our gamma facility in the high flux isotope reactor, or we can also receive material from commercial plants or ion irradiated material. We have our internal rabbit cask and other type of cask we perform to move things around our site, but we can also accept larger fuel shipments, commercial fuel, and a nat cask or other casks. And then they go to our hot cells. We've got our typical alpha hot cell, which you'll see everywhere else. We also have a relatively unique beta gamma hot cell, so you don't have to deal with alpha contamination when you're looking at your materials. And then we can package small samples or machine a section of a sample to get to subsized samples that we can then transfer to our radiological facilities with fancier instruments and systems for measuring thermophysical properties, microstructural examination on things that don't have quite the same dose rate that you couldn't necessarily put in a hot cell. Next slide, please. So let's talk about HFIR. So HFIR runs at about 85 megawatts, constant power. We don't go up and down at all. We run 85 megawatts until we can't. And
Hey, we lose Chris?
oh no, have I been muted the whole time?
No, I just cut out really fast.
Oh, good. Okay. So really, the reason you'd come to HFIR is that fourth bullet point in the plot on the right. We have the highest steady state neutron flux, at least in the U.S., and you can see that reflected on the right. Both fast and thermal flux, and our flux trap, which is that position on the far left, the PTP, peripheral target positions, and even in our reflector is still significantly higher than the other facilities that you would see here. And so that makes us a relatively economical option for a lot of materials irradiations. We can quickly put dose on structural materials, and we can quickly put burn up on fuels. The other thing I'll mention on this slide is that the reactor itself is funded by the DOE Office of Science for neutron scattering experiments in our beam lines. We are also funded to supply many of the world's radioisotopes. I say this because the relevance to fuels and materials experiments is that users don't have to pay for neutrons. As long as you publish results, we're a science lab. As long as there's scientific output, we don't have to pay for neutron fees, which is a nice advantage. Next slide. So here's the layout of the HFIR core. There are two annular fuel elements, the inner and outer fuel element with the red involute shapes you can kind of see in the center. And at the very center of the core is our flux trap. That's where we have the highest flux. That's where most of our materials irradiations are performed. Quite a few isotope production capsules are located there as well. As you move radially out from the fueled region, the sort of lighter blue region is our removable beryllium region. I'll talk more about that later. It allows convenient access for instrumented experiments for fuels and materials. And then moving out to the gray outer permanent beryllium reflector region, we have many positions for isotope production, but also for fuels because our thermal flux remains quite high out in those positions. Next slide. So in the flux trap, this is by far the most popular place for conducting irradiation experiments. The price you pay is that these are relatively small capsules, 9.5 millimeters, which is about 3/8 inch diameter by a couple inches long, or 60 millimeters. These can be sealed, so they're conducted in an inert atmosphere, or they can be perforated, so they're exposed to the coolant, which is a lot easier to get into the reactor, but of course you can't raise the temperature in any way. We've got about 100 of these positions. There generally is availability. Of course, the highest flux positions are going to be in more demand. If you want to do a partial cycle, we've got a hydraulic tube. You can see the video on the bottom right of us ejecting rabbits from the core. If you want to go a little longer, but not necessarily, you don't need a larger diameter, we can do longer length, 50 centimeter, roughly 20 inch long experiments that span the full length of the fuel. And then there are other examples, as you can see, metal tensile specimens is something we do very often. We can pack, tens of these inside of a single rabbit capsule and put dose on them very quickly. We can also expose materials to things like liquid metals, like you see there as an example. But generally, this is where we conduct our structural materials. And the reason is, of course, it's the highest flux region. We can get well over 10 dPa per calendar year in steels. And that's sort of our bread and butter, is putting dose on structural materials rapidly. Next slide. Now I'm going to talk about the other extreme, which is the permanent reflector position. So we have a high thermal flux out here. It doesn't drop off all that much. Of course, the fast flux is much lower, but this is kind of ideal for fuels experiments. And long ago, we came up with an irradiation vehicle that looks a lot like what you'll see in ATR to conduct integral fuel tests for light water reactor fuels. And we did a few of these experiments, but we realized that ATR is probably the better place if you want to do integral light water reactor fuel experiments, especially now with the addition of the coolant loops that they've added. But I think HFIR still has a role to play with fuels testing because of some recent changes we've made to modify that facility. And instead of loading a stainless steel target with full-size LWR fuel, we can load it with really any fuel you'd want that fits into a much smaller capsule. So what we call this facility is mini fuel. So if you can fit within a roughly 10 millimeter diameter by, I don't know, 7 inches, whatever that is in centimeters, I keep going back and forth. If you can fit within that volume, we stack about 6 capsules that are individually sealed. You can see those on the right. And within each of those capsules, you have very small fuel samples, whether that's a monolithic disk, loose microspheres or kernels, or trisoparticles. You can pack those into a small compact. We've done all these things. And the advantage to making the fuel small is, well, for one, the cost is much lower, but the other reason is we can really accelerate burnup accumulation without having to deal with large temperature variations and the complexity of understanding integral fuel performance with so many different variables that are changing. So we can assess basic performance, swelling, fission gas release very economically and very rapidly. And we don't even have to increase the enrichment. Our flux is so high that we can breed plutonium and we can get to at least LWR discharge burn up 6% FEMA within a calendar year just using natural uranium. So that really eases the burden on fuel fabrication. We don't have to deal with enriched uranium during the entire process of not just making the fuel, but assembling the experiment, getting it over to HFIR. It really makes things easier. Next slide. So sort of in between these two locations is our removable beryllium positions, which are my favorite position because they kind of have a balance of both worlds. You get a larger size, about 37 millimeters. You can have very long experiments that can be instrumented. And I say that because they have direct access from the vessel head. So we can drop sensors down into the experiment. So we've used these facilities for doing fuels and materials irradiations, but also sensor testing. The flux is essentially a factor of 2, both in thermal and fast flux is about a factor of 2 lower than what you'd get in the flux trap, but that's already extremely high. So you don't take a big hit in terms of flux and what you gain in size and instrument access. We've used these facilities long ago in the 70s through the 90s. We did over 20 irradiations for gas-cooled reactor applications, BISO, TRISO fuels, before the AGR program spun up. But it looks a lot like the AGR test, where we have a series of fueled capsules with in situ monitoring of temperatures and fission gas release. So we have the ability to do this. We haven't done it in a long time, but these are underutilized positions that have a lot of slide. And here's the latest RB experiment we've conducted. This is a sensor irradiation experiment called WIRE21. It's the most highly instrumented experiment we've performed in HFIR to date. We're primarily testing wireless temperature and pressure sensors that would go inside of a fuel rod for Westinghouse Electric Company. But we're also including thermocouples, distributed fiber optic temperature sensors, self-powered neutron detectors, and then passive silicon carbide temperature monitors and flux wires. So a lot of leads coming out of this experiment, and it really set us up well for bringing these instrumented leads out of these experiments using more, I guess, newer technology, not just thermocouples, but more advanced sensors. Next slide. And this is my last slide. I'm just talking about some examples of what we've done to support industry, at least within the last 5 or so years. So Kairos Power is working with us on an experiment that's wrapping up to irradiate TRISO compacts at higher power and lower temperatures that are more relevant to their fluoride high temperature reactor compared to traditional gas-cooled reactors. General Atomics has partnered with us in several projects. The first I mentioned is uranium carbide irradiations for their gas-cooled fast reactor. And then the other would be in the general area of 6-stick composites. The examples I show are cladding tube irradiations with a high radial heat flux for light water reactor cladding applications. The next one would be a similar application, light water reactor cladding, but evaluating radiation effects on cladding end plug, how you would seal a fuel rod, silicon carbide, and understanding if you retain hermeticity of fission gases under irradiation. And the last one is a less demanding application, more of a structural component like a channel box in a boiling water reactor, but the flux gradients in HFIR are actually convenient in this application to evaluate radiation-induced bowing of those materials. And then the far right examples are the 3 major fuel vendors in the US, Framatome, Westinghouse, and General Electric. Looking at things like coated zirconium alloy cladding, basic radiation effects on structural materials. I mentioned already the Westinghouse irradiation of their wireless fuel rod temperature and pressure sensors. And then the last is General Electric, trying to understand radiation creep, both in FECRAL alloys as well as coated zirconium alloys by pressurizing thin-walled tubes. That is it.
All right, hello everybody. So I'm going to give you a quick description of the MIT reactor. You'll notice that we are the only university reactor included here, and so full disclosure, we are actually not a test reactor. As a university reactor, we are a research reactor, and that does constrain some of the ways that we can test fuels, particularly in core. So I'll talk about that as we go along. If I could have the next slide, please. All right, so again, just a little bit of background. As was pointed out earlier, our MITR1 probably was the first of the reactors that you'll hear talked about today, which first went critical in '58. But our actual current reactor, and that's the one that you see in the picture on the right with the containment, our exhaust stack, and our old cooling towers, which have since been replaced. But we replaced the whole core and went from a heavy water cooled and moderated to a light water cooled and moderated heavy water reflector design in the early 70s. And we followed that up with a power increase from 5 megawatts up to 6 megawatts in 2010. So the current core, if you look down on it from above, is what you see in that bottom picture. So we've spent a long time providing neutrons for research in all kinds of areas, including physics, medicine, material science, nuclear engineering, and also training a lot of students. So we have student operators for the reactor, as well, of course, as a lot of faculty and students involved in the research that we do. A lot of the current focus of the MITR of our research program is on irradiation effects in materials and fuels, and also in sensors for application in current and next generation reactors. So pretty similar to a lot of the things that you've seen from the other reactors. So even though our fluxes are somewhat lower and we're a smaller reactor, our inclusion here amongst the test reactors arises from the fact that we we operate 24/7 and for fairly long cycles. So we're much in some ways much more similar to the test reactors than to some other research reactors. Next slide, please. Okay, so here's the basics of our reactor. We are a tank type reactor, and our power density is about the same as a current generation light water power reactor, PWR, BWR. We have forced light water cooling, but we're not pressurized. So we run at atmospheric pressure, and similar to the other reactors, also a relatively low outlet temperature around 50 degrees C. We use actually essentially the same fuel type as ATR and HFIR, the main difference being the shape of our fuel elements, and that is essentially this rhomboidal shape that you see in the core map here. And there's a picture of one of what our fuel element looks like from the side, and it is about 60 centimeters long. And the entire core is also about 60 centimeters across. So we're essentially a little bigger than a 5-gallon kitchen garbage pail. We have 6 large boron-containing control blades that are on the outer surfaces of our hexagonal core, and then a smaller regulating rod. So that gives us a cosine-shaped power distribution. The peak is just below the core axial midline because the control blades pull up from the bottom, so that presses that shape down a little bit. And as I said, we run long cycles, 60 to 70 day cycles for a year. So again, similar to ATR, we generally are shooting to run at least 200 and up towards 220 full power days every year. And if you look at the picture on the right hand side there, you see a couple of our typical in-core experiments in place in the reactor. So one is the water loop, which goes in through the reactor lid. Another one is the inert gas facility, which goes in and terminates underneath the reactor lid with any necessary instrumentation leads, so on, going out through the reactor core tank wall above the water level in the reactor. So again, these are pretty similar to some of the experiments that you've seen described in the other reactors. The major difference being that we only have 3 in-core positions in the reactor, and we almost always run those instrumented. So in-core, we really don't run the equivalent of drop-in capsules basically because with relatively few positions, we're almost always wanting to get the most out of them by running them with instrumentation coming out. All right, next slide, please. So this is just to emphasize a little bit this idea that our flux and spectrum is pretty similar to a light water power reactor. So you see on the right a quick graph of what our spectrum looks like compared to a PWR. So we're a little bit harder. We don't have quite as much thermal flux because the core design was actually made to be fairly leaky of fast neutrons because they're supposed to leak out into our heavy water reflector to feed the beam tubes. But other than that, you know, in the sort of damage producing area, we are pretty similar to a PWR. You can see some of our other positions listed there and the fluxes. And again, you'll notice that our fluxes are considerably less than in ATR and HFIR. But they are sufficient to, combined with our relatively long operating cycles, to get up to, you know, DPA levels of damage in a variety of materials in a year. And so, you know, especially for fuel applications where lifetimes are not all that long, we still are a very good place to do a lot of that research. And I'll talk about some of the other advantages of the MITR in a minute. All right, next slide, please. Okay, so our high temperature water loop has been a pretty major focus of our in-core radiation program for quite a long time. We have tested a lot of various kinds of cladding material. It does bring me at this point, though, to mention that you'll see that we don't do any fuel testing in our water loop, and that is a consequence of being a research reactor rather than a test reactor. And so in the core of the reactor, we are not allowed to test any fuel. We aren't allowed to put in any fuel other than our own reactor fuel, except if it rejects heat passively to our own reactor coolant. So it boils down to we can't put fuel into our water loop. We do have ways of testing fuel. I'll go over those in a minute. But we can, we do have the right irradiation environment, and we can create a wide variety of coolant environments to test cladding, and also to test instrumentation and to do some mechanical property kinds of testing as well. So what you see here is on the right, the two pictures that show the crack growth measurement system, which we've demonstrated. And this was done in conjunction with INL to look at adapting this system from a system designed by Halden, the reactor in Norway, which has since shut down, to adapt that for use both in the MITR and in ATR. And we did that successfully and have demonstrated this. So basically you use a high pressure bellows and the loading assembly that you see there to apply controlled, usually cyclic loading to a crack, and you can measure the crack growth in situ by measuring the potential drop across the sample. Then the bottom picture there shows a creep test facility that we used for measuring creep on silicon carbide composites. And so we tend to emphasize those kinds of experiments in that we aren't actually generally testing fuel, certainly not in the water loop. So we can also use the water loop if people need to irradiate samples at lower temperatures or very closely controlled temperatures at, you know, in the 350 C range by putting those samples into the water loop in sealed sealed capsules so that the samples are exposed to the radiation and at the right temperature, but without actual exposure to the coolant itself. Next slide, please. Okay, so again, similar to the other reactors that you've heard about, we also do a fair amount of work in inert gas irradiation facilities. Those are generally instrumented at least with thermocouples. For temperature control, we use a helium neon gas mixture. Nick described how that works for temperature control. So helium has about 8 times higher thermal conductivity than neon. We often use just the nuclear heating in the core to heat those systems, but we also can use electric heaters if necessary to provide greater control, or in some cases, for instance, in the Flux salt irradiations that we've done, in order to be sure that the salt doesn't get too cold if the reactor shuts down, because under those conditions, with the high gamma flux still remaining in core, you produce a lot of free fluorine, which is to be avoided. So that's one of the places where we first applied electric heating on our in-core experiments. But we also do a lot of work on instrumentation. You see an example on the right, a system that was used to test fiber optic sensors. We've also tested a lot of ultrasonic sensors, and you see also in that far right picture an idea that we often use of piggybacking just a materials irradiation test onto an instrumented sensor test, so that lower capsule with the cubes in it, those are samples of glass that might be used for making fibers, and the idea was to just look at the bulk changes in those glass properties at irradiation at controlled temperatures. The other experiment that you see there, which looks fairly complicated, was one to look at a thermoelectric generator, and so we were deliberately creating a fairly large temperature gradient across the sample using that graphite. The black section is a graphite heat sink, and that allowed us to test these thermoelectric generators in core. And the bottom picture just shows you what this actually looks like in real life. You see the that S-bend tube going down into the core, and actually right next to it, the open hole in the core. This was taken when the reactor was not operating, but that's the space where our water loop goes in through the lid of the reactor. Next slide, please. All right, so in addition to those in-core positions, we do have also positions in our graphite reflector, which is somewhat easier to access. We can do less than full cycle irradiations there more easily, and we also have fewer constraints on that, in the sense that we can run actively cooled fuel samples there, for instance, which we can't do in core. So right now we just completed some irradiations for some additively manufactured fuel that was produced at ORNL and irradiated at MIT, and we're also looking at a natural convection molten salt loop to look at the transport of radioactive corrosion products in the salt during operation. Next slide, please. Okay, so the one I also wanted to just mention fairly briefly, we are in the process of developing a large volume irradiation space. So in core, we have, a few centimeters diameter by maybe 50 centimeters long sample volume available, a little bit bigger than that in the reflector positions, but not significantly. But we have a fission converter that was originally used for boron neutron capture therapy, and that similar to a booster fuel idea, we take neutrons from the reactor, we run them into a separate tank with fuel elements, the same fuel elements we use in core, but in a a subcritical configuration. But we get a new fission spectrum there, and then we can run that vision spectrum, and we've just shown a very schematic idea of something that we could irradiate in there. Right now, the first experiment slated to go in there will be a fuel molten salt loop. Again, something that we are not allowed to run in core, but which we'll be able to run in this space. And we have the former medical room where the patients were for the BNCT system is available as a large shielded space for any of the support systems that we need for these types of irradiations. We also have planned, after the molten salt, we have a fusion reactor magnet irradiation plan for that space. Next slide, please. Oh, that's it. So I guess we'll move on to questions.
All right, I'm going to try and attack these in order. And first question is from Robert Hayes. Can you talk about the material damage in beryllium that requires its replacement in the ATR? So this is for you, Nick.
Yeah, can you hear me?
I can.
All right, so I'm not a material damage in beryllium expert, but I know it becomes embrittled. I think it's the N2N reaction in it that generates some helium. It eventually just becomes embrittled, and they need to replace it roughly every 10 years. It needs to be replaced. That's common. The BR2 reactor in Belgium and HFIR all have beryllium components that need to be replaced at about that frequency.
And then the next question is also for you. Radiation damage accumulation does not scale linearly with dose per displacements per atom rate. How do you correctly predict damage accumulation at lower dose DPA rates based on high dose DPA rate experiments?
Yeah, that's all right. Full disclosure, I'm a mechanical engineer, but I can definitely put you in contact with our people who specialize in that if you're interested to know. I really don't know the answer to that question. Sorry.
No problem. All right, and then next one is also from Michael Flus, and it's for Colby. How important are helium production and void formation during the high power pulse in treat in contributing to material and fuel performance?
Helium producing. So I mentioned the treat is typically not it's not a high fluence reactor. So any of these kind of reactions in their products are typically not a major concern or something that treat is used to investigate, given how low the fluence is in a given transient. So to accumulate any appreciable buildup of any kind of a reaction-based product, it's pretty minimal. So I don't know specifically if I'm answering the question, but I don't think that's something that's a major relevance in most of the things we do in treat.
And then I have another one from Michael, and this is for Chris. So 20 dPa in the high flux region in HFIR is the same as 20 dPa in a PWR. How do you account for dose rate effects in interpreting material experiments in HFIR?
Yeah, that's something we think about all the time. Anytime we're accelerating testing, rate effects are going to be important, whether it's for materials or fuels. And that's where I think, in a lot of ways, modeling and simulation is important for understanding recombination or other microstructural changes that time at temperature is not going to be the same. Like we have to rely on our material science expertise to understand and interpret results from accelerated irradiation, since we don't just do this in a vacuum. So I can't give a universal answer that applies to all materials, but it has to be done in combination with modeling and simulation.
So this is going to be more for all the panelists, and some of the answers might be a bit redundant, but we'll just go in the order of presenters. What kind of material limitations do you have to test in your reactor? If sodiums or thorium, whatever it may be. So Nick, you want to take that one first?
Yeah, that's a good question. At ATR, there are limitations on things that can be like in the primary coolant, essentially, things that would otherwise cause damage to the reactor vessel or mess with the chemistry. But for something that's contained in a vessel or a loop, there's I don't want to say the sky is the limit. There's obviously things that you wouldn't put in there, but we do have capsules that have a limited quantity of reactive metals in them. So we routinely do capsules with tens of grams of sodium in them. We done plutonium bearing, uranium bearing. We're even doing a test design right now with thorium bearing. So on the isotope side, there's no limitations. Essentially, every experiment gets analyzed for its unique hazards, and there's a whole process to show that it's within the safety basis of the facility. And as long as we're able to do that, then you know, virtually any material could be possible.
Perfect. Colby, same question to you.
I guess I would. A lot of what Nick just said is probably applicable as well on the treat side. There's no, I don't think there's any particular material that would be excluded explicitly. We consider on a case by case. There's some things that are more routine than other things, but you know, fuel materials of all sorts are routine in our facilities. You know, hazards associated with you know, a particular material would just be considered on a case by case, and we would always show that we are you know, handling such hazards adequately. If we can do that, it shouldn't be an issue.
Chris, would there be any change to HFIR and the materials that would be restricted at all?
Yeah, I think everything that Nick and Colby said generally applies. I'll just add a little bit and say that you know, like mercury, I know is not even allowed in the building because it can attack aluminum. And things like copper are generally have to be doubly contained. Things that might attack aluminum if they get into the coolant, it certainly can't be exposed to the coolant. The only other thing I'll mention with HFIR, it's a relatively small core, so there are sometimes reactivity concerns. So you wouldn't want to put a large amount of boron or some absorbing material, particularly in a hydraulic rabbit that's shuttled in and out of the core, because then you have reactivity, insertion, and injection concerns. And same goes for any experiment that could potentially move during the irradiation. We don't want to have strong absorbers, but for fixed permanent experiments, absorbers are fine. We irradiate, you know, gadolinium and cadmium and, you know, boron and all these materials as long as we can reject the heat adequately.
Perfect. Gordon?
Yeah, it's pretty much the same thing. Though, you know, we have the same concerns over reactivity. We have separate limits for what's classified as fixed, secured, and movable. So we have, if either something is designed not to move, but it might, or it can't, you know, it's very secured, or it actually is in fact designed to move. Those have separate reactivity limits, which we have to meet. So it does change the amount of certain materials that you can put in. Same thing, you know, we're also aluminum. We're an aluminum. You know, our fuel is aluminum. Everything is aluminum. So yes, mercury is is kept assiduously out of the reactor and out of the reactor building. The main difference, I would think, is that we do have a fairly strict limit on the total amount of sample fuel that we can put in. So we can only do 100 grams of U-235 equivalent per experiment, and if it's going in core. As I said, some of that, you know, that's not that limit doesn't apply in the reflector positions, and it won't apply in the new M-cube position, but for in-core, we do have that limit. On the other hand, that still allows you to make, you know, to make and test small rodlets of sample fuel. 100 grams is actually a reasonable amount of U-235 to put in.
Perfect, thank you. This one, just for the audience's knowledge, I'm going to leave it open to the group. Based on some of your previous experiments, what are some high-level kind of rough order of magnitude costs in the difference between a fueled versus non-fueled experiment or instrumented versus non-instrumented?
Yeah, cost. Again, I'm not a cost estimator, so nothing I say should be considered contractually binding. But generally speaking, you know, to design, irradiate, and do post-irradiation examinations, do a whole campaign on like a drop-in capsule, an instrumented capsule, and like, you know, like a full gas lead out. I don't know, numbers on the order of 1 to 2 million, 5 million, and maybe as high as $20 million dollars is typically what those things can cost. Obviously, number of specimens, number of exams, all these things cause giant the deviations from those numbers I just let out of my mouth. So don't take that to the bank.
I think it's a lot easier to project costs to get into the reactor. It's a lot more difficult to project costs for analyzing post radiation examination, because you may want to throw the kitchen sink at it. You may just want to cut it open and look at it. So I think getting into the reactor, for us at least, static materials irradiation experiments, no instrumentation, drop in, you could probably get away with a couple $100,000 to get into the reactor, but then it's the real cost coming on the back end. And then instrumented experiments could be a couple million to get in the reactor, obviously a lot higher on the back end.
Did anyone else on the panel want to add it to lead time? So go ahead, Gordon.
Oh, I was just going to say we're pretty similar. The absolute costs are somewhat lower at MIT, but sort of the escalation of costs as you add complexity, and certainly once you add fuel into it, costs go up in a hurry because you have to worry about where it's going at the end and all of the rest of that. So yeah, but other than that, yeah, fairly similar picture.
Did have another one from the chat. Is the ATRC of any particular value for the sort of testing being discussed here, or does it mostly support the ATR?
Yeah, ATRC, I did not mention, but is essentially a neutronic mock-up of the ATR core. It operates frequently. It's normally used for neutronic measurements, so to measure reactivity worth or flux changes from a given experiment configuration. It runs at low power for not a very long amount of time. We don't use ATRC for burn-up accumulation or fluence, right? But it is very useful. We frequently go to ATRC to do flux characterizations of the experiment before it goes into ATR, and it enables us to have more refined prediction and understanding of the neutronic conditions in the actual test that was irradiated in ATR.
Perfect. And I just wanted to ask the group as well, what are some different lead times for someone trying to get into, running an experiment in your reactor? And what are some kind of seemingly unexpected delays to that schedule that developers experience that we all kind of understand? Core change outs, operations maintenance, just a crane going down, let's say. If anyone would want to take that, feel free.
I would just say that generally speaking, design and fabrication of a capsule-based irradiation, something on the order of a year, is pretty typical. And it can be as long as 4 to 5 years to design, fabricate, and create a very complex experiment like an AGR test. What are the things that break that cause us uncertainty? So I don't know, everything in the plant. But I don't really have a good answer for that. It's I don't see any common themes. These are all aging facilities, but we really do our best to maintain them and keep them as reliable as possible.
Yeah, I think that hits the nail on the head. I think if you've got, there are examples where you can use something that's a design that's off the shelf, more or less, and in that case, if you're just fabricating parts and putting it together, you could do better than the 1 year timeline that Nick said. Maybe that's 4 to 6 months at best still, because you still got to get money in the door and start making stuff. But I think a year is about right for a new design, year and a half. And yeah, same thing with us. You never know what's going to go wrong. That's going to put us out for a couple months for maintenance or some unanalyzed issue that comes up that's just a paperwork issue, but it keeps you out of the reactor for a little while.
Yeah, I mean, I agree, and I would also say, in our experience lately, contracting is often an unexpected, you think, okay, it's the hard part is designing the thing and getting it built, and some of the times where we do some of that work at risk and we find we're ready to go in the reactor, but there isn't a signed contract yet because people are discussing various terms and so on. So there are ways to ease that. The NSUF contracts for us are very good in that regard, because that structure is already all in place, and it's really just filling out the blanks of what you're going to do for a particular program. But that is one that you really have to get started on that as early as possible and be as flexible as possible too in terms of getting contracts in place.
All right, Steve, I wanted to give you the opportunity to provide any final remarks before I wrap this up.
I think the panel here has represented the capabilities available in the U.S. for testing quite well. They are extremely diverse. All the reactors do some of the same things, but they all have unique capabilities where a particular type of experiment would drive you certainly to one over the other. But I would say the mix that we have taken together as a national resource really provides the advanced reactor community all the testing capabilities that they might need. So we would just encourage our industry partners to reach out to these gentlemen or their colleagues to get more information.
Perfect. I just wanted to remind the audience that this recording will be posted on the NRIC website as well as the slides. And I wanted to thank our today's presenters for getting this information out, and thank you for attending today's Tech Talk. And this concludes the presentation. Thank you.